video, we are going to discuss about pipelining. It is an approach to optimize the sequential circuits. So it is a popular technique which is often used in to accelerate the operation of the data path in digital processor. So here the basic idea is we need to compute, we need to take log of, okay, log of the output is equal to log of magnitude of A minus B. Okay, so for this one I'm going to take these two register in the A and B. It's represent the stream of numbers. Okay, so that is to be computed. So here the A and B is given to an adder. Okay, so okay, here so this A plus B. Okay, so it is given to an adder, and after that you need to take magnitude of this function. Then you have to take the log. After that it is stored in the register, and you are going to take the output. Okay, so for this one the minimum required clock period is the T minimum is equal to TSU. So SU represent setup time. Okay, and TCQ represent the propagation delay. Okay, of the register, and TPD logic it represent worst case delay path through the combination circuit. Okay, so what we are going to do, I am going to add and I am going to take the absolute value, okay, and a logarithmic function. Okay, so if you see here the delay associated with this normal conventional system is more. Okay, so in order to reduce the delay, okay, we are going for the pipelining. Okay, so it is a technique to improve the resource utilization and increase the functional throughput. So in the pipelining approach we are going to introduce a resistor in between this logic block. So if it is taking T minimum period for the conventional system, so you can see this this adder is active only for the 1/3 of the clock period. Okay, why? Because at a single time it is performing at a single time it is performing only addition. At the next time it is performing the absolute value, then it is performing the logarithmic value. Sure, that is between this logic block. Okay, you can see at the first time, at the first clock pulse, it is performing the addition of the first bit. Okay, at the second time it is not ideal. Okay, it is performing addition of the second bit, and the absolute value is performed at the during the second clock cycle itself. Okay, clock period itself. So during the third clock period we are getting the logarithmic output. Okay, so if you see effect of the pipelining is the clock period is reduced by 3 times. Okay. So I can take T minimum of the pipeline is equal to TCQ plus TSU plus maximum of this propagation delay of the addition and propagation delay of the absolute value and propagation delay of the logarithmic value. Okay. Because in the conversion system, only 1/3 of the clock period is utilized, remaining the 2/3 of the clock period is wasted. So therefore, that is why we are using for the that is why we are going for the pipelining one. Okay. So here we are obtaining this increased performance at the relative cost, small cost of this 2 additional resistors. Okay, and it will increases latency. Okay. So therefore, this pipelining is a popular approach in order to implement for the very high performance data path. Okay. So next one is latches versus register based pipeline. So we are going to construct the pipelining using the 11 sensitive latches. So instead of the edge triggered register, because of more flexibility and high performance it will offer. Okay. So it can be used, it can be implemented based on the past transistor logic. Okay. So this is a past transistor logic. Here I have utilized positive latch. Okay. This is the thing with a positive latch, and here it is nothing but a negative latch. So here it is here the logic which we have introduced is between the master and slave latches of the master slave systems. Okay. So here I have utilized 2-phase clocking systems. One is clock and clock bar. So here you can see if this is positive means this is negative. So this is how, and you have to note that both the clock and clock bar are non-overlapping. So if it is overlapping means it will end up in the race condition. Okay. So how it will perform means during the clock is positive. When the clock is positive, so the input values is sampled at the C1. Okay. So it get inverted, and the computation of the logic block F will start. So the result of this F is stored at the value of C2 during the falling edge of the clock. Okay. So next it get inverted, and the computation of this logic block G gets started. Okay. So for this one we have to ensure that we have to use the non-overlapping clock. So if we use some overlapping clock means there is a possibility of race get developed between the previous input and the present one. Okay. So this is the operation which I have told you before. So next we are going for the C-square MOS logic. Okay. So here this latch-based okay. So latch-based pipeline circuit It is also implemented using C square MOS logic. Okay. So this operation is similar to that one, but this C square MOS pipeline circuit is raise V. Okay. As long as this function f should be non-inverting. Okay. So what is the basic operation is during the when the clock value is 1. Okay. When the clock value is 1, and therefore the clock bar should be 0. So this input get inverted, right? So input get inverted, and this value is stored in this C1 value. Then the computation of f start. Then it will work as a master and slave city. So if this is so here it has to work as a master and slave, right? So once this process get completed, after that the slave will work. So my clock bar becomes 1 and 0. So okay, so the output of this get inverted, right? Get inverted, and that it is sampled in the C2. Then the computation of G2 get happened. Then this clock becomes 1. Okay, so again the inverted value gets stored in the C3. Okay, so what happens if there is a 0-0 overlap? If there is a 0-0 overlap, for the short duration of time, these two get to 0-0 value. So this value get this simply will go to the pull-up network. Okay. So the only way a signal can raise from stage to the stage under this condition is when the function f is inverting. Okay. So since there is a 0-0 overlap, okay. So this is a 1 and 1 overlap. Likewise, I can have 0-0 overlap. Okay. So for 0-0 overlap, if this is inverting, so inverting means if I am going to connect I have connected a inverter. Okay. So during this time, my clock and clock bar is 0. Okay. So this will goes to 1, and this will goes to 0. Again, this 0-0 will happen. So I can see this 0 will end up in 1. Okay. So you can see 0 get changed to 1. Okay. So this will result in a race condition. Okay. So the similar conditions are valid for 1-1 overlap also. So what I'm going to do is I'm going for a NORA and C square MOS logic. So for NORA logic, I'm going to implement the dynamic logic function, and for a pipeline register, I'm going for a C square MOS logic. So it is a mixture of static and this is my static logic, and this is a mixture of static and dynamic logic. Good. So for logic function, I'm going to use NOR, and latch I'm going to use the C square MOS logic. Okay. So the logic and latches are clocked in such a way that both are simultaneously either in the evaluation, or it should be in the pre-charge or hold mode. Okay, so this is for clock module. Okay, this is for clock module. Okay, so this is a NORA function. You have N and P logic. So whenever I give the clock is equal to 0, it get pre-charged to 1. Okay, so NORA logic goes to pre-charge node. Okay, so since the clock is 0, this will be in the evaluation phase. So this is 0 here. Okay, so this is 0 means and you can see the value of clock. The clock is 0 here. Okay, if it is 0 means this will be open circuited. Okay, this will be open circuited. So the output is in the hold mode. Okay, so next I am going to give 1. So if I give the clock as 1, so it will be in the evaluation mode. So if this is the evaluation mode means this will be 0, and here get pre-charged to 1. Okay, so this will be 1. Okay, now my clock is 1 0. So this will be 1. So it will be in the evaluation mode, right? It will be in the evaluation mode. Okay, so next you can see for the clock bar module. Okay, so during the clock bar module, so you can see this is the NORA logic, and this one is a C2MOS logic. So here I have used static logic also. You can see this is an AND gate and this is an inverter. Okay, so whenever the clock is 0, okay, and this red color line it get this goes to 1. Okay, since it goes to 1, this goes to evaluation phase, right? So the NOR logic is in evaluation phase. So this 1 will reach here. So since the clock value is 0, can write it as evaluate. Okay, next when clock is 1, when the clock is 1, this will be goes to 0. Okay, this orange line will goes to 0, and this will be pre-charged, right? This will be pre-charged, and you have 0 here and 0 here, and then this will be in the hold mode because this entire thing is open circuit, so it will be in the hold mode. So the NORA data path consists of a chain of alternating clock and clock bar module, right? So you can see this here you have a clock and here a clock bar module. So if one class of the module is speed charging means the output of the latch in the hold mode, right? One is speed charge means another one is in the hold mode. Okay, so which will preserve my previous output value. Okay, so the other classes is evaluate. Okay, so this is how the data is passed in the pipeline fashion from module to module. Okay, so this NORA offers a designer a wide range of design choice. So since dynamic and static logic can be mixed freely, and both the clock P and clock N dynamic block can be used in the cascaded or in the pipeline form. So with this freedom of design, extra investor stages required in the domino CMOS logics are often avoided.